Welcome. In this lecture, we're going to be talking about minerals. We're going to go over some basics of chemistry, how minerals are forming, and then talk about the physical characteristics of minerals, which you need to know. So again, minerals are a very important thing for us to start on because they do um, come together in groups and they make up what we're going to be learning about as rocks. So they make up those aggregates of rocks. So no lecture of minerals is possible without understanding exactly what a mineral is. So I'll just hold up one example for you if I can grab one right here. So I've just got a nice little mineral sample. So all minerals are naturally occurring. So they form out in nature by natural processes. They are inorganic. They are solids, they're not liquids or gases. They have a very specific ordered internal structure that creates the crystal structure that we see. So they form the same way all the time. And they have a very distinct chemical composition. Now, the chemistry can have a small range to it, but the elements that come together in the same ways, in the same amounts, and that's why they have that specific ordered internal structure. All right. So again, I mentioned that we can't actually talk about any of this without talking a little bit about chemistry. So what we see on the slide in front of us is the periodic table. And what I really want you to take away from this is that it's just a big listing of all of the elements that we see on the Earth. Elements are substances that cannot be broken down into simpler substances by any physical or chemical means. Okay. Further, when we talk about chemistry and we talk about elements, we talk about atoms. So atoms are the smallest particle of matter that retains all of the characteristics of an element. So we're looking at two different diagrams. We have the flat view on the left and kind of the three-dimensional drawing on the right. And this is just two ways that we can sort of imagine an electron. In both cases, we see that there is a nucleus at the center, and the nucleus is where the protons, which are the positively charged particles, where those are located. Protons have mass and a positive charge. The yellow here is representing a neutron. Neutrons have mass but no charge, but again, it's the protons and the neutrons that are located inside of the nucleus. Now, surrounding that nucleus are the electron shells, the valence shells. So in the flat diagram, we're just seeing those as circles. The inner circle is going to be filled when there are 2 electrons on that inner shell, and then every outer shell after that is considered filled when there are about 8 electrons in those shells. Now, the flat diagram is very easy for us to see and understand, but what's really happening is very dynamic. So atoms aren't just like hanging out with the electrons in perfect spots. The electrons are moving around constantly, and they actually do jump shells back and forth. So chemistry is much more exciting than sometimes these drawings let us see. Okay, so some other basic things, and again, what you can see here is another look at what an atom looks like. But basically, some basics of the chemistry that you can take out of that periodic table is how it's organized. So everything has a symbol for the element. So we're looking at helium, which is represented by a big H and a little e. It has an atomic number at the top, and that's how everything is ordered in that periodic table. The atomic number tells you how many protons are inside of the nucleus, and that number doesn't change. In order for it to be helium, it has to have 2 protons. If it has more than that or less than that, it will be a different element. Okay, the mass number is the bigger number on the bottom, and this just tells you the weight of that atom. So the atomic weight is determined by the mass of all of those protons and all of those neutrons added together. All right, and the last thing are isotopes. Isotopes are atoms that have the same number of protons, so it's the same element, but they have a different number of neutrons. So their atomic weight will be higher or lower depending on which isotope that you're looking at. This will come into play when we talk about radiometric age dating, so we'll come to that later. All right, so some more basics of chemistry. When we're talking about minerals, we're actually looking at compounds. So a compound is a substance that's formed by the combination of 2 or more elements, and the elements come together through a process of bonding. Bonding is the transferring or sharing of electrons so that atoms can become stable. So when we talk about stability, we're actually trying to look at, and I apologize, my picture's right in front of this, so we can look at part of this diagram. But this is just telling us how many electrons are in those valence shells. So again, the inner shell, as it says right here, has 2 electrons, and then once it has those 2, it's completely full. The outer shells will have 8 electrons, and then they are full. When the valence shells are full, then the atom is going to be stable. When they are not full, then the atom is going to want to find a way to fill that extra valence shell, and that happens through a process of bonding. Okay, so there are 2 types of bonding that we're going to talk about with geology and minerals, and that is ionic bonding and covalent bonding, and those are both shown here. Ionic bonding happens when we see that the atoms are transferring electrons to each other. When they transfer the electrons to each other, they become more positively or negatively charged, and then it's that positive and negative attraction that brings those 2 elements together and holds them together. These ionic bonds tend to be pretty weak. So what we're looking at as the kind of the classic example of ionic bonding is that of sodium and chlorine. If you have your lab kit, you can pick up sample number 6, okay? All of the bonds that are happening inside of that sample are ionic bonds. This is actually halite, which is sodium chloride, shown up here. So what's happening when we're looking at this, sodium has 11 protons in the nucleus and 11 electrons. It starts out with that in the shells. So it ends up with actually 1 extra electron that's kind of hanging out there. So it has 2 electrons in the middle and then 8 electrons in the next shell. And then it has a second shell with only 1 electron. And that sodium is like, hey, you know what? I don't really need this electron. It's going to take me a long time before I can fill that. And so it actually can send that one out. It's like, hey, you want this? You can have it. When it lets go of that electron, that sodium becomes positively charged. Okay. Chlorine is, let's see, let me make sure I get the number correctly. Chlorine is 1 electron short, and so it actually wants to have an extra electron. I'm going to try to make sure I get the correct number for you. So it has 17 electrons in it. So it needs 1 more to fill that extra shell. And so what it does is it's like, hey, anybody got an extra electron? It grabs that, it pulls it in. Well, now it has 1 more electron than protons. It becomes negatively charged. And so then the sodium and the chlorine, they are then attracted together and they hold together. Now, ionic bonds, again, are not super strong. So these electrons, we can pull these apart. We can stick this halite in water and it's going to dissolve. Again, because of those charges, they're going to break apart pretty easily. The second type of bonding that we see is covalent bonding, and that's where the 2 elements start to share electrons. Because they're sharing electrons, both of the atoms want it, and they tend to hold on more tightly together. So the example that we're looking at is a bond between chlorine and chlorine. Another mineral that has some very strong covalent bonding would be diamonds when we look at the bonding between carbon. So, excuse me, in this case, we again still have 17 electrons. So both of these chlorines need 1 more electron. And what's happening in this case is this chlorine's like, hey, I need 1 electron. And this one's like, hey, I need 1 electron too. When they come together, they're like, well, if I use your electron and you use my electron, then we're both filled. So that's kind of what's being shown right here in the yellow where they're kind of overlapping. So it's kind of like these 2 atoms are really tightly holding hands. They both want it, or it's like a tug of war between 2 kids over a toy that they both need to have. So those end up being some very strong bonds between them, and they're a lot harder to break.